covering lecture 4, summary calculation of thermodynamic properties. The point of this lecture was to show you that even though on your equation sheet you have these over here, you have all of these equations here. Can we transform them to have actually measurable thermodynamic properties, which is temperature, pressure, volume, CV, and CP. So the point of this lecture was to actually derive these equations from these equations here, and also using Maxwell relationships. So we just recalled you know, how du equals TdS minus PdV, and this is the equation for the first law of thermodynamics, where du is actually represented in terms of all the thermodynamic properties: temperature, entropy, pressure, and volume. And it incorporates the first law, and inherently it incorporates the second law because it has ds as well. And this is a basic equation of convenience, and as back in the day when they derived these equations from the experiments, they saw that as internal energy increased, entropy increased, and also the PDV volume also increased. So U is actually a measure of the quantity of energy that the system possesses, we'll discuss this later in the other lectures, but entropy tells you how much quality you have of that energy. Then, from the canonical variables of internal energy, you can derive, using Lagrange transforms, these following equations here. But actually these equations arose out of definitions, and they were defined as a matter of convenience. But all these equations here that appear here and on your equation sheet are the legitimate thermodynamic equations. So H is enthalpy, A is Helmholtz, and G is Gibbs energy. And for this system here, when we differentiate both sides and write it with respect to U, you'll see that this is just from the energy balance, but chemists like to use this equation because they work in beakers, so volume and temperature. But as us chemical engineers, we're going to be using the Gibbs equation more later on, because we measure pressure and temperature with regards to flow processes. So this is written for the entire mass of the system. I don't have the copies on it, and these are all exact equations, and they are general equations for homogeneous fluids or that have constant composition. And then you do have these identities here, definitions and identities, where this T equals du ds is the thermodynamic definition of temperature, and P equals du by dV negative is the thermodynamic definition of pressure. And then from these, because T and P are part of the USV, from these definitions of temperature and pressure, you can further derive a definition of S and of V with respect to H and G and A and G and T. And it all comes about from the criteria of exactness, and exactness also helps us, and it's nice because it gets you Maxwell relations. And the Maxwell relations will actually, you use these in deriving the thermodynamic equations with respect to more of temperature and pressure as opposed to entropy. So I've rewritten it here. Can you see the left hand side? It all has temperature, volume, temperature, pressure, pressure, temperature, volume, temperature. And you'll see, like in your thermodynamic equations, the first 6, they have entropy and volume, and you can't really measure entropy, but you can measure temperature and pressure and volume. So you'd want to, the point of deriving Maxwell equations was eventually so that we can use them to transform our thermodynamic equations into thermodynamic properties. These are the bases of the derivation of Maxwell equations. You can actually get many more. So over here, the heat capacity, this this is the definition for CP, and this is the definition of CV. And where it was defined by, it's defined by the, well, dHdt was actually defined by the function H is a function of temperature, and internal energy was defined by F is a function of T and V. So using saying that this is an exact function, you can write the total derivative, and saying that this is an exact function, you can write the total derivative, and you'll actually derive dH equals Cp dt, where Cp dt equals dH dt, and for this one as well. So you can try that. But the whole point of the lecture was to actually get to deriving thermodynamic equations, which was dHCp. This is one of your equations, and this is one of the equations. And it was using H is a function of T and P, and S is a function of T and P to derive dH and ds with respect to Cp, VT, and as well as ds into Cp, TV. And using the definition where Cp equals T ds dt. Right. Was that correct? I think so. Yes, it was. Yes, because if you look at the total derivative. But essentially it was where Cp also, you rewrote it, and eventually in your derivation you found out, like if you were in class, that equation 5 equaled this. So what the aim of the lecture was to do was to actually find the temperature and the temperature differentials, derivatives next to it, and replace it with the measurable data. And you can go through all those steps where it's just substituting in your Maxwell's and rearranging the equations. And yes, your Maxwell equations, they can be found by you applying the exact definitions to your definitions of your identities. So all these identities and Maxwell equations are essentially just identities to help you transform your thermodynamic equations into measurable data. So these two equations you see on your equation sheet, and then you can also derive this equation, which is not in your equation sheet, but it was just to show that you can be a function of p partially derivative, but this is not on your equation sheet. But these two are on your equation sheet, and it was further shown that by replacing in your, when you go u equals utv, you write the total derivative for this one, and you write the total derivative for this one, you can get your, you can replace your temperature differential and your pressure differential with these here into measurable datas, into measurable equations. So basically, you can find an equation for ds. And then what you notice from the equation for ds, when s equals a function of t and p and s equals a function of tv, because we evaluated for t and v over here, and earlier you evaluated for t and p, you can actually equate the equations and get the difference in heat capacities. So essentially what you need to walk away from in lecture 4 is the appreciation for knowing where the equations on your equation sheet come from. So let me just write them, particularly like these equations over here. So it's getting appreciation for, it's getting appreciation for where these equations came from. So these equations over here, du equals cv dt, tp dv, it was derived in this lecture, and that's what you just need to walk away from. But it's nice because all of these terms here in those equations help you to find equations that you can apply in other applications when you do have measurable data. So so for example, if I have du equals cv dt plus t dp dt tv minus p dv, this is one of your equations. If you have cv data and you have an equation of state that says how pressure changes with temperature and but you keep volume constant, you can plug it into here. And if you have no expression for pressure and if you have expression for temperature, then you can substitute it into these placeholders. So these are actually, this is a placeholder, this is a placeholder, this is a placeholder, and this is a placeholder. All you need is an expression describing CV, an expression describing P, an expression describing T. And those are essentially your equation of states, and then one of them is your ideal gas. So one of them is your ideal gas, where your PV equals nRT. And near the end of one of the slides over here, you can prove for an ideal gas that Cp minus Cv equals R. So you can try and prove this in your own time for an ideal gas, and this slide followed this over here, relationship between heat capacities. So you can see that this is a placeholder and this is a placeholder. All you have to do is use the mathematical operation by partially differentiating the expression P with respect to T and partially differentiating the expression V with respect to T and substituting in for T as well. And you can get a relationship of Cp Cv minus Cv. And then another useful expression I was just mentioning was that Cp over Cv equals gamma. And that's an expression you'd use, and you'll tell me more about it in your assignment. Yeah, this was just to say that if you partially differentiate the ds equations, the two ds equations, that, because ds is given in terms of Cv and Cp, which is really cool, because you can calculate if you have any of those data, you can find out more about it if you have an expression, and this is really cool because it's just in terms of temperature and pressure, or temperature and volume. Nothing else is required. You don't need entropy. These useful terms here, volume expansivity and isothermal compressibility, if you look in the equations in your equation sheet, you could just replace dV dt and dV dP in your equations for liquids. So these equations are valid for liquids. And yeah, you'll see the little handout again in class, which is also uploaded on under slides for this section, that you'll see that they use these beta and kappa to write it for liquids. And you'll find out that for liquids that they're a weak function of pressure. Right. So essentially what you learned in this lecture, what I want you to walk away from, is that by using what you know about canonical variables and Legendre transforms and Maxwell relations and identities, because you can use those identities to find Maxwell's, and by exactness, the criteria of exactness, you can find and if you know the definition of what Cp and Cv is, the thermodynamic definitions, you can rewrite these equations here in terms of measurable thermodynamic properties, and that's temperature, pressure, volume. Yes, and yeah, now you can be confident to read other textbooks and the manipulating the data. Yes. And what this slide was here essentially was saying was, we started off fine strokes of explanations, but as we go on in the thermodynamics, they're going to be quite broad strokes, and you just need to keep up with the momentum of it, because these broad strokes actually relied on the fine strokes inherently. So if you know your notation, you know your maths, you know your identities, you know that you can use these thermodynamic equations, then you're on a good track, because in the next lecture, lecture 5 and 6, it uses these thermodynamic equations because these are measurable data equations.